Magnetic fields 5. This is the last video in quite a big topic, and it's about transformers. So why do we need transformers? Well, look at this circuit. We have a power supply and a bulb. The power supply maybe represents a power station, and the bulb represents a factory. Now, if your factory is next door to the power station, no problems. If your factory is a distance away from the power station, then you've got a problem there, because you're going to lose energy in the transmission cables. On this diagram above, you're losing voltage. Okay, energy is lost in the transmission cables, and that reduces efficiency. Your transmission cables get hot. Now, how can we make this system more efficient? Well, power is voltage times current. To deliver the same power, if the power is the same, you can either have a small voltage and a large current, or you could have a large voltage and a small current. Now, which one will be more efficient? And the answer is the second one. Why? Because the power lost in the supply cables, we can say, is I squared R, where I is the current and R is the resistance of the cables. And as it's I squared R, then if the current is big, we're going to lose lots of power. So the idea is the best thing you can do is keep the current small. So if you use a very large voltage and a small current, it is more efficient. So we use a step-up transformer to make the voltage bigger, then we transmit it, and then we use a step-down transformer to make it small again. How does a transformer work? I suggest you learn this word for word. An alternating voltage is put across the primary coil. An alternating current flows in the primary coil. This produces alternating flux, which flows in the iron core, and alternating EMF is induced in the secondary coil. You've got a primary coil and a secondary coil. They're joined together by a laminated iron core. How does a transformer work? Learn that. Okay, this equation here, V out over V in, is NS over NP. A step-up transformer, which makes the voltage bigger, has more turns on the secondary coil. A step-down transformer has more turns on the primary coil. And the ratio of the number of turns is the ratio of the voltages. Now, as I said earlier, the voltage from the power station is stepped up before going onto the national grid, and then the voltage from the national grid is stepped down before domestic use, because in your kitchen you don't really want 400,000 volts in your kitchen, or there'll be big lightning bolts jumping out at you, killing you probably. It has to be AC. This is one of the big advantages of AC, is that it can be stepped up and stepped down. You can't step up and step down DC, which Edison wasn't very happy about, and so Tesla won that one. If a transformer were 100% efficient, then the power in would be equal to the power out. So V times I in would equal V times I out. So if you're making the voltage bigger, then you're making the current smaller. If you're making the voltage smaller, then you're making the current bigger. If the voltage is stepped up, then the current must be stepped down, and vice versa. And so the equation gets a bit more complicated. V out over V in is NS over NP equals I in over I out. Okay, why are the cores of transformers made of laminated iron? What do I mean by laminated? Thin sheets of iron separated by an insulating glue. Why is this necessary? Well, if you think about how a transformer works, iron is a conductor. We don't want EMFs induced in the core. If you get EMFs induced in the core, what will happen is you'll get things called eddy currents. Eddy currents flowing in the core. And the eddy currents will, not only will the core get hot, and that will reduce the efficiency of the system, but the eddy currents in the core will kind of fight against the flux that you're trying to produce. You'll get less flux. So we use a laminated core to reduce eddy currents in the core, which would have a heating effect and reduce the efficiency of the transformer. And lastly, I think this is a transformer question for you to have a go at. Pretty straightforward. Have a read, have a go, and the answer is that.